To see beneath the surface of tissue, we have to understand the fundamental light interaction mechanisms with tissue. There are two processes that can occur. Light absorption, which is attenuation by molecules within the tissue. The dominant ones are hemoglobin, water, and lipid. Light scattering, which is a change in refractive index, both between cells and within cells, that will cause light to scatter. In wavelengths between about 400 and 600 nanometers, light scattering is dominated by Rayleigh scatter, where the particles that are scattering are small with respect to the optical wavelength. In wavelengths above 600 nanometers or so, the light particles are large or comparable to the optical wavelength, and scattering falls off as approximately 1 over lambda, which is me-like scattering. In this regime, multiple light scattering dominates light propagation, and scattering lengths are on the order of about 20 microns, whereas absorption lengths are much longer, on the order of about 10 centimeters. In this region where multiple light scattering dominates, if we launch light into tissue, we can actually measure coherent interactions up to a depth of about 1 millimeter in tissue by capturing back-reflected coherent light using gating strategies such as interferometric, holographic, or geometric gating. They allow us to preserve the coherent information content and suppress the multiply scattered light. We can go deeper in tissue by looking at multiply scattered photons. And here we treat photons as particles. We'll typically use a transport equation-derived model to measure the intensity or temporal spatial fluctuations of incoherent light and capture deeper tissue structures.